Hello everyone, welcome to the next session of Laplace Transform. In this video, we are going to see how to find out Laplace transform of derivatives. Say f of t is given to you and you are asked to find out Laplace of its derivative, that is f dash of t, or double derivative, that is f double dash of t or f triple dash of t. Now we are going to see how to get its Laplace. So in previous sessions we have seen four properties. This is our fifth property, Laplace transform of differentiation. So if f of t is given, how to get Laplace of f dash of t, f double dash, f triple dash of t, and we can extend this formula for nth derivative of t. So here Laplace of f dash of t is nothing but s into Laplace of f of t minus function's value at t equal to 0, that is f of 0. Similarly, Laplace of f double dash of t is nothing but s square into Laplace of f of t minus s f of 0 minus f dash of 0. Similarly, the Laplace of f triple dash of t can be obtained. Now, we can observe the formula. If it is first derivative, you can see the power of s is 1. If it is double derivative, it is s square. And if it is triple derivative, it is s cube. All these terms are attached commonly with Laplace of f of t, or you can call it as phi of s. And then first term is positive and all other terms are negative. Then it contains reducing power of s like s cube, then s square, then s, and then s raised to 0, that is 1. Similarly, Laplace of f of t, then f at 0, f dash at 0, f double dash at 0, and so on. By these observations, you can definitely form the Laplace of fourth derivative of function, that is Laplace of f fourth derivative at t can be taken as s raised to 4 as it is fourth derivative, Laplace of f of t, then we have minus sign, all other terms are negative, then reducing power of s raised to 4, that is s cube, f at 0 minus s square, f dash at 0 minus s, f double dash at 0 minus s triple dash at 0. So this way we can extend the formula for higher derivatives of f. Now let's see few examples on this. The first example is find the Laplace transform of f of t, where function is given sin t upon t and we are asked to find out Laplace of f dash of t as well. Okay, so we know that Laplace of any function, say f dash of t, is nothing but s into Laplace of f of t. We are using first formula here because first derivative is expected, minus f at 0. We call it equation 1. But for this derivative, we need Laplace of f of t. So f of t is given here as sin t upon t. So we'll go first for Laplace of sin t upon t. Now again we can observe here 1 by t is a property available in the function. That's why we leave it for a moment. So we target our remaining function, that is sin t and its Laplace. So we start with Laplace of sin t. We know it is sine of at, so value of a is 1 and its Laplace is a upon, that is 1 upon s square plus a square, that is 1. When we attach that property division by t on left side, that is sin t upon t, what is the effect on right side? Right side is integrated in the limits s and infinity with respect to s. So 1 upon s square plus 1 ds. Its integral is the tan inverse of s upon 1, that is s only, in the limits s and infinity. When we put upper limit s as infinity, tan inverse infinity gives us pi by 2 minus lower limit s is s, that's why tan inverse of s. Moreover, we can write this as cot inverse s. So this is what our Laplace of sin t upon t. So first part is over. We call it phi of s because this is our f of t's Laplace. Now for second part, that is Laplace of f dash of t, we have equation number 1, that is s into Laplace of f of t, but f of t is here sin t upon t, whose Laplace is already done, minus f at 0. Here f of t is sin t upon t. So what will be f at 0? F at 0 is nothing but, it seems that it is sin 0 upon 0 and that will be indeterminate form, but we know there is a standard formula for limit as t tends to 0 for sin t upon t is nothing but 1. That's why f of 0 value is 1. Therefore, we can use it here that s into Laplace of sin t upon t is a cot inverse s. So cot inverse s minus f of 0 is 1. So this way we can find out Laplace of some f dash of t. So using the properties of Laplace transform of derivatives, we can find out Laplace of f dash of t, f double dash of t, and even higher derivatives. We have one more example here, that is find out Laplace of derivative of 1 minus cos 2t upon t. Okay, so here property is expected. You are not expected to find out first the derivative of the function and then take its Laplace. Though the answers are matching, but that is not expected. We have ready formula here. So this is first derivative, that's why again first formula will be used. And what is the requirement of that? We need to have Laplace of f of t first and function's value at 0, that is f of 0. So here same thing can be written as Laplace of f dash of t is expected, and here f of t is nothing but the function 1 minus cos 2t whole divided by t. Again we can see here 1 by t is a property, so numerator we will start with. So Laplace of 1 minus cos 2t, both functions are in standard form. Laplace of 1 is 1 by s minus Laplace of cos 2t is s upon s square plus 4. So Laplace of numerator is over. Let's attach property on left side, that is 1 minus cos 2t upon t. The effect on second side is integrated in the limits s and infinity. So it will be 1 by s upon s square plus 4 with respect to s. So we know its integral is a log of s minus, here derivative of denominator is a 2s which is missing at numerator, that's why we multiply and divide by 2. So it will be half of log of s square plus 4 with the limits s and infinity. We have already discussed this situation. Same thing can be written as log of s upon root of, this half of log becomes log of root of s square plus 4, and this, since this is log of a minus log b form, it gives us log of a upon b form. So s upon root s square plus 4, still limits we have not applied, that is s to infinity. Okay, now if we take s square common from square root, so we will get here s outside, that s will be cancelled with numerator s. So remaining term is 1 upon root 1 plus 4 by s square, and that time when we apply s as infinity, 4 by s square gives us 0, and remaining term is only log of 1 which is 0. So with this discussion we get upper limit value 0 minus lower limit is s is replaced by s, that's why the term as it is s upon root s square plus 4. To consume this minus sign, we can have the property log of a upon b is nothing but minus of log b upon a. So we have root s square plus 4 at numerator and s at denominator. This is what Laplace of function only, that is Laplace of f of t. So we call it Laplace of f of t. But this was not our target, this was our requirement for the formula. So you can see this formula, equation number 1. So here Laplace of f of t was required because the question is find out Laplace of f dash of t, that is derivative of 1 minus cos 2t upon t. So this is nothing but s into Laplace of f of t, which is phi of s for us, minus f at 0. Now let's have a look on how to get function's value at 0. So we have f of t given to us, that is 1 minus cos 2t upon t. When we apply t equal to 0, we get 1 minus cos 0. Cos 0 is 1, so 1 minus 1 numerator is 0 upon 0. So indeterminate form. We get here indeterminate form. So using L'Hopital rule, what we do? We, before applying limit, we take derivative of numerator, that is 2 sine 2t upon 1. That time when we apply t equal to 0, we get sine 0, that is numerator is 0 and denominator is 1, and that's why overall we get it 0 as t tends to 0. Okay, so using L'Hopital rule we get function value at t equal to 0 as 0. Therefore, we can continue here. Therefore, this is nothing but s into Laplace of f of t. Laplace of f of t is log of root of s square plus 4 upon s, and that's it. Let's have third example on this. So in this example, the function is splitted given that the function has value t in the range 0 and 3, and if value of t is 3 onwards, then function takes the value 6. So function is splitted, range is splitted here, and we are asked to find out Laplace of such function and also Laplace of its derivative. So we'll go first for Laplace of f of t. So by definition of Laplace transform, we have Laplace of any function, of course satisfying certain properties. Laplace of f of t is nothing but 0 to infinity e raised to minus st f of t dt. Let's use this property for given function. So Laplace of given function f of t is integral. Now 0 to infinity will be splitted into 0 to 3 and 3 onwards. So when limits are 0 to 3, function value is given as t dt, plus when t varies from 3 onwards, so function's value is 6. So e raised to minus t into 6 and dt. So 0 to infinity is splitted as 0 to 3 plus 3 to infinity. Now with usual integration method, we will solve this. So this is something u into v form. So first as it is, we are taking t as algebraic first term as it is. So t as it is, integral of e raised to minus st is e raised to minus st upon minus s minus derivative of t, which is 1, and one more integration of second function, that's why e raised to minus st upon minus s, and previous minus s is s square. This is called generalized rule with the limits 0 and 3. Plus here 6 is constant outside and only single function e raised to minus st, so integrated as e raised to minus st upon minus s in the limits 3 and infinity. Now for upper limit, first term gives us t equal to 3, so minus 3 by s e raised to minus 3s, we are putting t as 3, minus e raised to minus 3s upon s square. This is upper limit value for first term, minus lower limit, put t equal to 0, so first term gives us 0 because of multiplication by t, minus when put t equal to 0, we get e raised to 0, which is 1, so 1 upon s square. This is what about the first term integral, plus second term for upper limit. Now e raised to minus infinity, but e raised to minus infinity is 0, that's why now e raised to minus infinity can be written as 1 upon e raised to infinity, and that's why 1 upon infinity, which gives us 0. So upper limit gives us 0 here, minus we have lower limit, put t equal to 3, so minus 6 by s and e raised to minus 3s is the lower limit term. When we open all the brackets, we get
minus 3 e raised to minus 3s upon s minus e raised to minus 3s upon s square plus 1 upon s square plus 6 upon s e raised to minus 3s.
Okay, so these two terms can be clubbed because of common denominator. So minus 3 times e raised to minus 3s upon s plus 6 times the same is giving us plus 3 times. So finally we get
3 times e raised to minus 3s upon s minus e raised to minus 3s upon s square plus 1 upon s square. This is our Laplace of given f of t. This is a Laplace of given f of t. Now we will go for Laplace of its derivative. So
Laplace of f dash of t is nothing but s into phi of s. Phi of s nothing but Laplace of f of t minus f at 0. So function's value at 0, you can observe here f at 0. So when t equal to 0, that value of t comes in this range because t is varying from 0 to 3. So when t is 0, function's value is a t. Therefore function's value is a t. And when we put t equal to 0, we get f at 0 is 0. Therefore when we put these values here, the Laplace of f dash of t is nothing but s into phi of s, that is 3 e raised to minus 3s, plus 1 upon s square, plus 1 upon s square. This is what about the first term integral, plus second term for upper limit. Now e raised to minus 3s upon s minus e raised to minus 3s upon s square plus 1 upon s square. So upon s minus e raised to minus 3s upon s square plus 1 by s square. That's it. So this is the final answer for given function. Thank you everyone. So in this lecture we have seen that if f of t is given and we are asked to find out Laplace of its derivative, maybe first, second or third or higher derivatives, we can use the formula given.